Okay, so first little proposition. If we're in a two-connected plane graph, so graph drawn in the plane, plane graph is an entity in its own right. In a two-connected plane graph, every face is bounded by a cycle. So that's 426. 426, G-plane, two-connected for every face. The boundary is a cycle. Right. Okay, so let me prove that. If the entire graph is a cycle, then that's true by Jordan. Right? So we need that. So it's not as trivial as it looks. So let's assume that there is something else. And the graph is not just a cycle. And we know how to construct all the two connected graphs, starting from a cycle. Right? So, and the thing to do was to start with a cycle and then add h paths, where h was the subgraph of G previously constructed. So at first h is a cycle, then we add an h path, and then we add another h path, and so on. So let's do induction by the number of steps we need to construct our G. Okay, so let's look for the induction step. Let's look at the the last step in this construction. So we have this h, to which we added an h path p. And h has some other stuff in there. And now h has a face that contains the interior of P. Why is that? Because every 2 points on P are equivalent in plane minus h. Because along P you can find a polygonal arc between any 2 such points. So this is a set of pairwise equivalent points, and therefore contained in some equivalence class a face of h. Let's call that f prime. Yes, because we've got an f here. Right, so this f prime has nothing to do with this f. Okay. Now, first case, the boundary of f is in fact a subgraph. We know it's a subgraph of G, so it's not half an edge. And first case, this is actually a subgraph of H. And then we know that f is also a face of H. That was an earlier lemma. And therefore, by induction, the boundary of that face is a cycle. Done. Okay, case 2. Well, if the boundary of f is not contained in H, it must contain a point of G that is not in H. And which are the points of G that are not in H? Those points. So that's the boundary. Yeah, so this, I mean the point set now rather than a graph. It's so frontier of f has a point on P. Right, that's the other case. Okay. Now this little p is a point in f prime. Choose a little open disk around it that lies entirely in f prime. Then, like every open neighborhood of little x, because x is on the frontier of f, this has a point in f, by definition of frontier. Okay, but since this disk avoided, or sort of lies entirely in f prime, this little point lies in f prime as well. So f and f prime have a non-empty intersection. Now, f lies in some face as a subset of some face of h, because it's a face of G. H is a subgraph of G, right? And the face of the bigger graph is contained in the face of the smaller graph. So f lies in some face of H, and that face must be f prime, because it meets f prime as I've just shown. And so the faces of H prime are all disjoint equivalence classes. So f is contained in f prime. Okay, now let's see what we can say about the entire boundary of f. I claim that this is contained in C union f prime. Now, why is that? C is the frontier of f prime by definition. So this is a closed set. If this had a point outside that closed set, that point would have a neighborhood avoiding this set, because the complement of a closed set is open, right? So a point of this boundary of f outside this would have an entire neighborhood outside this. But that's not possible, because every neighborhood of a point on the boundary of f has a point in f, by definition of frontier. But f is a subset of f prime, so it also has a point in f prime. Okay, so we know that. But of course, this is also in G, right? Boundary of f is a subgraph of G. But we know what this is. Right, what does G have in C union f prime? What does it meet in there? Well, it contains the entire C, fine. And what points from f prime does it contain? Precisely P, interior of P. So that is C union P. Now, the boundary of f is entirely contained in this subgraph of G. But then f is also a face of that subgraph. Ancient lemma, one of the earliest lemmas. So f is a face of this. But we know what this looks like here. And we know what these three paths between here and there, along C, and P, they form a theta, and we have the theta lemma to deal with thetas. So the faces of any theta are bounded by two of those paths, namely a cycle. So we need to wheel in this rather heavy-handed theta lemma to complete the proof. Okay, questions? Okay. Next proposition. We know that in the two-connected graph, the faces are bounded by cycles. And now we can ask which cycles. Is there a way of characterizing those cycles combinatorially without looking at this point set in the plane to say, yeah, all the cycles of length 7, perhaps. Something that we can phrase without reference to the plane. That's the aim now. Can we characterize those cycles that do occur as face boundaries amongst the entire set of cycles in a two-connected graph? So here's a caveat. If we have 2 points, 2 vertices, and the entire graph looks like this, lots of independent paths between these 2 vertices, u and v, then the blue cycle, which bounds a face, and the yellow or the orange cycle, which doesn't bound a face, are combinatorially indistinguishable. Right? So if you look at this as an abstract graph, so every plane graph defines an abstract graph. What is this abstract graph? We have 2 points and lots of paths between them. And there are no 2 of those paths that are more equal than the others. Right? So, that looks tricky. And indeed, we don't have a combinatorial characterization in this case, but if we assume 3 connectedness, then we do. So this is 4 to 7. 4 to 7, if G is 3 connected and plane, so I mean G is a plane graph whose associated abstract graph is a 3 connected graph, and C is any cycle in G, then we can say whether G is a face boundary or not. Do I want to introduce? No, I don't want to do that. C bounds a face if and only if G is induced and does not separate G in the graph sense. Right? The whole point is that this is a statement that doesn't refer to the plane. That's a combinatorial statement about graphs. And we call such cycles peripheral cycles precisely because they bound faces. So they're on the sort of outside when you draw this graph in the plane. And notice that this makes no reference to how it's drawn in the plane. Indeed, we shall prove that there's only essentially one way of drawing a unique, a three-connected graph in the plane. That will come next time. So, yeah, here are many ways of drawing this. So we could flip these paths over. And sometimes such a path lies on a face boundary and sometimes not. Yeah, don't worry. Okay, so let me prove that. Let's prove the backwards implication first. So if C does not bound a face, can we show that it's not induced or separates G? Right, and well, here is C. If it doesn't bound a face, yeah. So I'm proving this implication.
Yes, I know, but shouldn't it be and does not separate G because it says and does not?
Thank you. Yeah. Okay. Right, so let's prove the backwards implication by contraposition. So we're assuming that C does not bound a face, and let's show that it's not induced or separates G. So if it doesn't bound a face, C in the plane, or in a plane graph, is a circle. So this does leave separate, topologically, it separates the plane into two components, inside and outside. That's Jordan's, the Jordan curve theorem. So there is something in here, and there's something out there. If there's a vertex inside and a vertex outside, then C separates these vertices topologically. So any arc from here to there must hit C. That was one of the prelims. But then, of course, also if this arc is in fact a path in G, it has to hit C, and it can only do that in a vertex. So C also separates in the graph sense any two such vertices. Okay, so that's fine. And if there's not a vertex in each of the two faces, but some other points, what can other points be? Well, inner points of edges. Right? So such an edge, if it doesn't have a vertex in this component, then vertices must lie on C. So this edge can't cross C. Otherwise, it would have to have an inner point on this subgraph, and of course it doesn't. So we have a plane edge connecting two such vertices. So we have shown that C is not induced. Right? There is an edge. Okay. Now, the other direction. So let's assume that C bounds a face, and let's show that it's induced and does not separate G. Well, it's certainly induced. If it wasn't induced, there would be an edge here. This is the face that it bounds. Right. But then these two vertices would separate any vertex from here, in here from any vertex in there, and they exist because this edge is a chord. So it's an edge that contradicts the intended result that C is induced. So if C is not induced, it has a chord. It has an addition. There is an additional edge that's not an edge of C in the graph, and here it is, running outside this phase. But then, by the theta lemma, any path from this vertex to that vertex, which also has to run outside this phase, would somehow meet an inner point of that edge. And that can't be, so these two vertices would separate those two in the graph, but then the graph will be reconnected. Okay? Right. Okay, so let's show that C doesn't separate two vertices. Let me draw the face outside. So C bounds a face. Here it is, let's see, drawn here. And we have to show that it doesn't separate two vertices. So pick any two vertices. Well, they can't lie outside because that's a face of G. And when I say separate two vertices, I mean obviously two vertices not on C by the definition of separate. So they lie in the other face of C in the plane. Right, now I'm going to show you two proofs. This is the pedestrian obvious proof. In the plane, you can get from one to the other without hitting C. Why? Because these 2 points are equivalent in plane minus the circle C. Now that's just a polygonal arc. We would like there to be a path in G that avoids C. And yeah, but that's sort of messy and easy at the same time. We have our graph here, right, like this. And now we want to somehow convert this arc to a path in the graph. And every time we cross from one face to another, say here, we say, okay, we ought to walk around here, and rather from here to there, we ought to walk around here, and so on. So it's possible and easy in elementary topology to convert this arc into a path in G, and that's what we want. Right? We want to show that C doesn't separate the graph. That's the pedestrian proof. And here's a brilliant, totally bizarre proof, alternative proof. Let's start with these two vertices. Let's call them X and Y, and draw a completely different picture. Now we have X and Y in a three-connected graph. And since you've been dreaming about Menger's theorem for the last 3 nights, obviously, you will say, yeah, but then there are these 3 paths from X to Y. One of them might be an edge. But now, let's hunt for F. Where is F? F is a face. So The union of these three paths is a subgraph of G. So F lies in a face of that subgraph somewhere. That's our little F. But then, that's a tiny little topology again, but really, really easy. Just the definition of Francia. Call that face of the union of these three paths that F lies in, call that F prime. So we know that F is a subset of F prime, and then when we take the topological closures, that is preserved. Right? That's just the definition of Francia. And therefore, F plus the boundary C lies inside F prime and its boundary. Now, its boundary by the theta lemma is the union of two such paths. That vindicates my drawing it like this. I shouldn't have really drawn it like this because we don't really know that F doesn't have a little bit of here and a little bit there and a little bit there, but now we know. Right? So the closure of F lies in the closure of F prime, and the boundary of F prime is a cycle in this theta graph. It's a union of two of those three paths. And there, look at this. This beautiful third path joins x to y without hitting F. Yeah? And I like that proof because it needs a totally different approach. And this is what you obviously do. You have 2 points, and you look at what you have, you draw what you have, and then you say, okay, here are my points. I want to get from here to there. How do you get from here to there? And here you just take completely different approach. And then you start with 3 connected, and you wheel in Menger somehow because you've been dreaming about it. Questions? Good. Now, when we have a plane graph, we can maybe make it bigger until we can't make it any bigger. And the graph we get to, the plane graph we get to when we're stuck, is called maximally plane. Right? So G is a plane graph. G is maximally plane if we can't add a plane edge and maintain that drawing, extend that drawing to extend that plane graph to a bigger plane graph. Right? And then G is maximally plane. Right? You can also call the entire G a maximal plane graph, but then maximal doesn't refer to plane, it refers to plane graph. If you wanted to refer to plane, which is really more precise, then it's maximally so, it's maximally plane. Similarly, a graph is planar. So we have plane graphs these objects that I defined last time, and we have something called planar graphs, which I haven't defined yet. That's an attribute of abstract graphs. So plane graphs give rise to graphs, in our sense. Those graphs that occur here are called planar. Conversely, an abstract graph is called planar if it's isomorphic to some plane graph, maybe to many. Always too many. You can always wiggle the plane graph a little bit and make it into a different plane graph by rerouting the edges a little bit, but also substantially different, maybe in the case of those 4 or 5 paths joining 2 points. There are 2 very different ways of, as we say, embedding that graph in the plane. There are, or isomorphisms of that abstract graph to a plane graph, very different ones. Okay, so are you clear about the difference between these 2 things? So plane graphs are things by themselves. A plane graph is a pair v comma e, where v is a subset of the plane, finite subset of the plane, some points, and e is a set of polygonal arcs in the plane such that blah, 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 blah. A planar graph is any graph that is isomorphic to some plane graph. Okay, now you can ask whether a graph that is maximally planar is also maximally plane once you have drawn it. And the answer is yes, of course, because if you could add a plane edge in that drawing, then the associated graph would be a supergraph of this. That's still drawn in the plane, and therefore that supergraph would also be planar. The converse is less clear. If you're maximally plane, you have a plane graph, and you can't draw another edge. Is the associated graph also maximally planar? Or might you have chosen a bad drawing? So might it be possible to look at the graph that you have drawn, just look at the associated abstract graph, shuffle it around, and then redraw it in some way where you can add another edge? That's very much a non-trivial question. And the answer is no, that can't happen. And that's what I want to show you next. So maximally plane graphs are also drawings of graphs that are maximally planar. They're not maximally plane because we chose a bad drawing. Okay. So here's 4 to 8. A plane graph is maximally plane if and only if G is a so-called plane triangulation. It's usually called a planar triangulation. Maybe it shouldn't be. Anyway, so that just means that all faces bounded by triangles. Okay. And of course, G has to have at least 3 vertices. If G is a K2, then it's clearly maximally plane once you have embedded it in the plane, because there's nothing more to connect, and it doesn't contain a triangle even, but it does have a face and the face has a boundary. And this is now, at long last, to prove the Euler formula. So let me start with just a little bit of hand waving about surfaces. Just a little bit of background. As I said, surfaces do appear in graph theory unbidden. In graph minor theory, they occur in the characterization of minor closed classes of graphs, graph properties, whether we like it or not. So, but surfaces are sort of topologically totally understood and easy to deal with and so on. They're no more difficult than the plane. Indeed, that's due to their, well, no, but they are. So what are surfaces? Here are some examples of surfaces. Let me just draw some pictures. So that's the sphere. Right? My best drawing of a sphere. Then we can have a torus. That's something like a rubber inner tube of a bicycle wheel. So then we can have a double torus that looks a bit like this. Right, can you see that? Yeah. You can have a triple torus and so on. So you have lots of examples of what we want to call surfaces. Now, what's the definition of a surface? We'd like to say one of those things, but what are those things? So this is one of these classical problems that occur in mathematics all the time, where you have to come up with some concrete definition, precise phrasing that uses only things that you've defined before. And here the definition is very, very simple. You might know it. It's a topological space. I'm not defining that. Look it up. That is compact. You know that definition. And locally homeomorphic to the plane. So that means every point in this topological space has a little neighborhood. What's a neighborhood is part of the definition of topological space, has a little neighborhood, open neighborhood that is homeomorphic to the entire plane. So intuitively, take a little point and has a little open disk around it here. I mean, it's totally undefined. It's just a picture. And this disk is the same as the plane. And the same here, and so on. But that is the entire definition of surface. Now, lots of questions. Are these things surfaces? Unclear, because I can't say what these things are. There are other ways of making this picture precise, and then it turns out that it does satisfy that, but that's all we can say. What we can ask is, are they all distinct? Are any two of those homeomorphic, whatever they are? And the answer is they are distinct once we've made the definition precise. And I want to get to why they're distinct in just a moment. And another question is, are they all surfaces? So is every topological space that's compact and locally homeomorphic to the plane one of those? And the answer to that is nearly. Right, so it is possible to take one of those surfaces there, assuming we've defined them properly, and cut a little disk out, okay, sort of cut this out, and then identify opposite points. By identify, well, what I mean, yeah, so these are deleted, these points in here in this open disk, and then this and this become 1 point, this and this become 1 point, and so on. And then you have to check that in this newly defined topological space, and there is a definition of that, it's called the quotient topology, and so on. It is still true that locally around every point, and one such point is now a pair of these, for example, or this pair, has a little neighborhood that is homeomorphic to the plane, and the neighborhood of this would be sort of half this. This is, in the torus itself, has such a neighborhood, and we just take one of this half here, and its counterpart up there, if you look at all these points as they got identified, so the upper points here get identified with the lower points there, and these two together, they make another little disk in the identified space. So you can make all that precise, and then what you get is not one of those. So up to doing this once, all the surfaces are indeed the ones that I've shown you, but that's something one has to prove. So why are they distinct? And that is Euler's theorem. Chi is the Euler characteristic, chi as an characteristic, of a surface S is defined as, well, believe it or not, n minus m plus f I'll tell you what they mean in a moment, is an invariant of S. And what does this mean? This means embed a graph in this surface, in this topological space, as we embed graphs in the plane, same kind of definition, and do it in a sort of sufficiently dense way. Choose a sufficiently dense graph so that every face is bounded by a cycle. So every face, no, sorry, that's even too strong. So that every face is homeomorphic to a disk. Right? If you embed a tree here, that's fine. The complement of the tree is homeomorphic to a disk. All right? So for every graph that has this, it satisfies this very weak requirement that every face, every equivalence class of points of the surface minus that graph is a disk, and then you count the number of vertices, and you subtract the number of edges, and you add the number of faces, then you always get to the same number that depends only on S and not on the graph. Totally bizarre. But this is sort of the, or one of these showcases for the use of invariance. Right? Now we can prove that two surfaces are not the same surface, are not homeomorphic to each other, simply by embedding graphs in the two and doing the counts and coming to a different value. Right? So otherwise, try to prove that two topological spaces are not homeomorphic. You'll be in trouble. Right? Make a list of all the maps from one space to the other and check whether they're continuous and inverse is continuous and so on. Right? These topological spaces are big. Right, so, yeah. And we're going to prove this, our theorem is this for S the sphere or equivalently the plane. Equivalently up to 1 point. You may have seen that in your analysis course. I'm not going to go into that. Right. So questions about this little introduction? Okay, then let's prove Euler's formula. We've already done that once in a way that shows you how not to do it. And so our claim now is obviously that we can do it better now. And let's hunt for, I'm going to show you the same proof essentially, but let's look where we needed all those lemmas, these terrible pedestrian lemmas that I've been giving you in the course of that proof. Okay, so n minus m plus f is 2, right? And so you get 2 here, you get 0 there, you get minus 2 there, and so on. And when you do one of those, you get the odd numbers. Yeah?
So 1 is minus 4, minus 6, minus
Yeah, yeah. Yeah, that's one of these things in intelligence tests, right? You're given the 7 numbers and you're asked to produce the 8th number. There are many ways. Maybe if you're too clever, you come up with the wrong answer. So, yeah. Okay, so induction start, proof induction on the number of edges. If n is, I write at most n minus 1, our graph G is connected. Okay. If m is at most n minus 1, it is in fact n minus 1. It can't be any smaller if n is, if the graph is connected. Then it is exactly n minus 1, and then the graph is a tree. And for trees, we verified Euler's formula. Right? Trees have exactly one face and one more vertices than edges. And we proved that they do have exactly one face. And that was one of those things that were not entirely trivial. Okay. So now induction step. Now m is at least n, so it's bigger than this, and we can use the assumption for smaller n. And now we try to do the same proof as last time. And let me just draw some picture and show you some notation. So we picked an edge last time. Last time I said just pick an edge. Now I said pick an edge on a cycle. And then we want to call the graph minus that edge G prime. Our graph is called G. And now we know that since E is on a cycle, it lies on the boundary of precisely 2 faces. It took us a long way to get there, right? They're exactly two faces, f1 and f2 of G, such that the boundary. Now, I'm allowed to write E as an element of this graph, right? I write that for vertices and for edges in abstract graphs. Okay. So E is on the boundary of F1. It's also on the boundary of some F2. And Fe is the face of, I think I want to call it Fe. Yeah. Face of G prime containing E, the inner points of E. Right, G prime is G minus E. So in G minus E, in the drawing, all the points, the inner points of E are pairwise equivalent, so they all live in the same face, and we'll call that face Fe. Okay, so important remark here. It looks as though Fe is, well, so there's a little more, so that might be C here, right? Sorry, we don't have a C. There's some graph here, some G. Right? And it might be tempting, and that's what we did last time, to say Fe is the union of F1 and F2. I said these two faces merge to make one face. Now how do we do this properly? Well, we're defining now Fe as a face of G prime. G prime is properly defined. Therefore, Fe is now properly defined. It's the face of G prime that contains all these inner points of E. F1 and F2 are also properly defined, except we don't know which is which, but it doesn't matter. So they are the two faces on whose boundary E lies. And now we can any questions? No. Right. Now we can do the following calculations. We'll prove that G of F, no. Right, F of G. That's the set of faces of G. F of G, except those two, without F1 and F2, is the same as F of G prime minus Fe. And once we have shown this, then we're done, because this is the set of all faces of G. So the number of faces in this set is 2 less than G has faces, because we're taking 2 away. The number of faces here is 1 less than G has faces. Okay, so once we have shown that all the other faces of G are precisely all the other faces of G prime, then G has two more faces than this joint number, and G prime has one more faces than this joint number. And therefore, since G also has one more edge, namely E, the count follows from the count for G prime, the induction hypothesis. Right? So this is an equality of two sets of subsets of the plane. So let's just prove that. If we take a face of G, but not one of those two. We know that it's a set of points whose boundary lies entirely in G prime. Why is that? We know the boundary of this lies entirely in G because it's a face of G. But G has more points than G prime, namely it also has this edge E. But the boundary of F not only doesn't contain E, it doesn't even hit E in a single point. That's by this lemma which I paraphrased as saying the boundary of a face isn't half an edge. Right? So we know that these two are not only the only two faces that contain E, they're in fact the only two faces whose boundary contains E, but they're in fact the only two faces whose boundary has an inner point of G. Now we're considering another face. The boundary of that face has no inner point in E. I kept saying in G, in E. Right? So, the boundary of that is in fact in G prime. So F is a face of G prime. If G prime is a subgraph of G, F is a face of G whose boundary happens to lie in this subgraph, and therefore, as one of those early lemmas says, F is in fact a face of this G prime. But it isn't this face, because this face, Fe, contains the inner points of E, and F certainly doesn't, being a face of G. Okay, done. That was easy. Other implication. Now let's take any face of G prime. Let's see what I want to call it. Yeah. F prime. F. But not this. Let's consider any face in this set, and we have to show it's a face of G, but not one of those two. Well, is it a face of G? Yes. Then there exists a face of G such that F prime is a subset of that F. Now, this looks like the wrong way around, right? So when you have a graph and a subgraph, the faces of the big graph are contained in faces of the subgraph. And now we have a face of the subgraph, and I'm claiming that it's contained in the face of a big graph. But that is, in this particular case, due to the choice of this particular face of the subgraph, namely that it isn't this. So what is it? This is a set of points of the plane that doesn't contain any point in G prime, and it doesn't contain any point of E, because only this face contains points of E. And a subset of the plane that contains no point of either G prime or E is a subset of the plane that avoids G. So it's part of some equivalence class of such points, and that's what I call F. Yes, but by the other argument, we also know that F is a subset of some face of G prime. Now, this is the right way around. So G prime is the smaller graph, G is the bigger graph, and every face of the bigger graph is contained in the face of the smaller graph. Okay, but what do we have now? Now we have one face of f of G prime, and we have another face of f prime, of G prime, and this is supposed to be contained in that. And that can't be if the faces are distinct, so they're the same. So in particular, there's equality here and there's equality there. So f prime is in fact equal to f to some face f of G. We don't know very much about that face yet. And we want to show it's not one of these two. That's all that remains to show. But it can't be one of those two, because those two have the inner points of E on their boundary. And since this is also a face of G f prime, its boundary doesn't contain points of E. Right, because E isn't in G prime. Okay, so that is the proper proof of Euler's formula. And I hope you feel sort of slightly, or I feel slightly vindicated now in making you suffer through all these details of elementary topology. I hope that you see now why this is, at least in principle, a really precise proof, given those very, very few preliminaries that we had, like Jordan's curve theorem. And also, you saw all the pitfalls on the way there. So you saw that the hand-waving proof wasn't just not quite exact, but really morally a good proof. Yes, morally by a very, very wide sense of morality it was, but yeah. Questions? No, then I give you just one corollary. Oops, wrong way. Okay. So I have it down as 4 to 10, but it's quite possible that some of these statements that I'm going to give you are not formally in there. So 1 every plane or planar triangulation has exactly 3n minus 6 edges, where n, as always, is the number of vertices. Yeah, and that has a pretty proof. Sort of when you look at a planar triangulation, you have all these faces, they're all triangles and so on. Right? And sort of every edge lies on some face boundary, on some a triangle, and lies on another triangle. So it's counted twice, but every face has 3 edges. So somehow the number of edges, every triangle contributes 3. So the number of edges is 3 times the number of faces, except you count every edge twice. So it should be 3 over 2. Right, and how do we make that sort of informal reasoning precise? There's a very simple way to do that. We draw a bipartite graph. And here we have the edges, and here we have the faces. And then we just make an edge incident with a face if it lies on the boundary of that face. Okay? So every edge lies on the boundary of exactly 2 faces in a plane triangulation. And every face has exactly 3 edges on its boundary. So this graph has 3 f edges. F is the number of faces. And it has also 2 m edges. Namely, for every edge lies on 2 faces. And if you work this out together with the Euler formula, this one here is 2. The 2 has disappeared. Whoa. So there's the 2. All right. Then this comes out. Right, you need two inequalities, 2 equalities, Euler's and this little thing here, and then it just pops out. Then next assertion is the plane triangulations, or no, I want to phrase the other way around. A plane graph is maximally plane if and only if it has 3n minus 6 edges. Well, if it's maximally plane, then we know it's a plane triangulation, and therefore it has 3n minus 6 edges. Conversely, if it has 3n minus 6 edges, it has to be maximal, otherwise we could add an edge, then we'd get a bigger plane graph. And that bigger plane graph, well, we could make it even bigger to make it really maximal, and then that would be a plane triangulation again, and that would have 3n minus 6 edges. So you can't have 3n minus 6 being strictly bigger than another 3n minus 6. So that's fine. 3 is that every planar graph has at most 3n minus 6 edges. So this is an abstract graph that is isomorphic to a plane graph, has at most 3n minus 6 edges. Yeah, same reason. You can make it plane, it's isomorphic to a plane graph, and that plane graph has at most 3n minus 6 edges. And now the interesting bit is that the maximal planar graphs, or those graphs that are maximally plane, the maximal or planar graphs, or maximally planar graphs, are those with 3n minus 6 edges. So if it's maximally planar, it has at most 3n minus 6 edges, and it can't have more because it has a drawing, and that drawing has at most 3n minus 6 edges. And conversely, if it has 3n minus 6 edges, then it's clearly maximally plane. So in particular, a graph isn't maximally plane only because it was badly drawn. The reason we cannot add a plane edge is not that we should have drawn it differently, because no matter how we draw it, we still have a planar graph, and that can't have more than 3n minus 6 edges. So if our plane graph already has 3n minus 6 edges, then it's maximal not only with respect to that particular drawing, but really with respect to fitting in the plane. And I think that's all I want to say. Any questions? Super. Thank you.